Hi Noah, we didn't have time last time to get this one, this number 15. This is 0.060 molar H2SO4. There's two H's there, so there are two Ka. First Ka is for the first H, and then you get HSO4 minus after that H falls off. Second Ka is for the next H. So the HSO4 minus loses an H, you get SO4 2 minus. Let's do the problem. I sent you an email about this, but I wanted to get it to you in a video that you could just watch, you know, on your phone, at your leisure. So here is the first dissociation. Now you notice that this is a strong acid, one of your 6 or so strong acids, and it's only like that for the first proton, the first H plus to fall off. This is just one arrow, not a double arrow. So there's no equilibrium. There's no ice chart to do because the dissociation is complete, of course. So if you have 0.060 molar of H2SO4, it's going to dissociate completely into 0.060 molar of H3O plus and 0.060 molar of HSO4 minus. So that means the pH, I mean, if this were the only thing that were happening in your solution, the pH would be 1.22, because 1.22 is the negative log of that thing right there, 0.060 molar. And you notice that this is one of the answer choices. Oops, wrong one. You notice that this is one of the answer choices, like this one, 1.22, C. But you know, I don't think that's correct. It's a good approximation, but if you're trying to be accurate with some precision, you want to also consider the other proton falling off. The other proton is this. Here is this product here, this conjugate base of H2SO4. It is an acid, a weak acid, not a strong acid. So here we are. You may not need to see this video. If you were able to just figure all this out from the email that I sent you or from some comments that your teacher has made in class by now, that may have obviated the video, so you know, I really don't mind if you ignore it. I just want to be kind of complete for you, you know? Alright, so this is our new equation. This is the new chemical reaction that's happening because we've just found that 1.22 would be the pH just from the strength of the acid H2SO4. But now, here is the second proton coming off. That's the second proton. Oops, that's the second proton right there. And now, because this is a weak acid, I'm going to use the ice chart. Ice. Okay, so this is 0.060 molar, and this is You remember, this was also 0.060 molar, which is why the pH right now is 1.22, right? And this is nothing. Okay, so because there's a 0 here, the reaction is going to go this way, meaning the change is going to go minus x plus x plus x. So at equilibrium we have 0.060 minus x. We have x. Oh nope, that's not x. Sorry, and 0.060 plus x, and we have x. Now they give you the Ka, which is 0.012. 1.2 times 10 to the minus 2, and Ka equals H3O plus times SO4 2 minus divided by HSO4 minus, right? So I'm going to substitute in the equilibrium value for H3O plus, which is 0.060 plus x, and then the equilibrium value for SO4 2 minus, which is just x, and the equilibrium value for HSO4 minus, which is 0.060 minus x. Okay. Now, of course, an approximation here would be that you can just ignore the minus x, right? So for the next 2 minutes, I'm going to talk about the approximation. Sometimes you can approximate that the idea that this 0.060 is going to be much larger than this x, because if the Ka is very, very low, like 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, something like that, the x is going to be very small because the change is going to be very small. Not much is going to, not much of the reactants are going to go to make products. So what does that mean? That means any x that you subtract from 0.060 is going to be insignificant. Also, any x that you add to 0.060 is going to be insignificant. So in such a case, you would be able to cancel these out. They would just be 0.060. This would be 0.060. This would be 0.060. And 0.060 divided by 0.060 is just 1. And so x would equal 0.012. Now, did you get that? If you choose to make that approximation, because this is a multiple choice question, then you're going to get x equal to 0.012. And if you get x equal to 0.012, then you can find the pH right away, because the pH is the negative log of the H3O plus concentration. So the pH is going to be the negative log of 0.06 plus x. 0.06 plus x, which is 0.06 plus 0.012, because, oh, sorry about that, I forgot to write that x equals 0.012. So that's going to mean the negative log of 0.072, but that's a 7. The negative log of 0.072 is 1.14, and that's one of the answer choices. So these AP people expected you to make this approximation. I disagree with the accuracy of that approximation in this case. And I disagree because this Ka is pretty big. It's 10 to the minus 2. 1.2 times 10 to the minus 2. I only make this approximation when the Ka is 10 to the minus 5 or smaller than 10 to the minus 5. So I suggest that you ask your teacher if he has some kind of rule of thumb for you to go by. When can you make this approximation? X is so small that it won't affect 0.060, whether you subtract it or add it, you know? So 0.060 minus x equals 0.060. When can you make that approximation? Let me show you what this problem would look like the way I would do it, where I don't make that approximation because I believe that this Ka is too large to make that approximation. Will I get a different answer than 1.14 for the pH? Will I get a more accurate answer? I say yes. And let me get you another page here. Okay, so I'm not going to make that approximation. So 0.012 equals, what was it? It was 0.060 plus x times x divided by 0.060 minus x. So I'm going to say the x is not going to be so small that this difference is insignificant, or that this sum up here is insignificant. So that means I have to do the entire multiplication. So I'm going to cross multiply 0.060 minus x equals, and then I'm going to distribute the x here and here, you know. So 0.06x plus x squared. So now this is an algebra problem. It's not chemistry anymore, so to speak. So 0 equals x squared. This times this is going to get added to this. So plus 0.072x minus, now this times this is going to get subtracted on both sides. 0.00, let's see, 1, 2, 3, 4, 5. 0.00072. Okay, now here's a quadratic equation. You would use your calculator to solve this. I don't have such a calculator, so I'm going to use the quadratic formula. This will take just a few seconds, I hope. B squared minus 4ac over 2a, and that is going to be negative 0.072 plus or minus. Okay, I've done this work in advance, so let me share that with you there. Oops. Okay, sorry about that. Here we go. So here is that work that I've done in advance there for you, and okay, so you could see that everything's kosher here, and the answer that I get in the end, I'll bring it up for you here. There it is. There's the answer in the end. Everything ends up being about 0.009. Okay? X. When I say everything, what I mean by that is X. So X ends up being 0.009. It's really 0.00897 something, but I don't care about the significant figures because this is a multiple choice problem, and I just have to pick the well, actually, well, I'll just keep it like this. So, so now, where was that work? Here we are. So x ends up being, so blah 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 blah. X ends up being something like 0.009. So when x is 0.009, you could see that the previous x that we had used with the approximation, is 0.012. So there is a big difference between 0.009 and 0.012. Let's see how that difference affects the pH. Let me erase this a bit for you there. Okay. So when x equals 0.009, that means that H3O plus equals 0.06. Remember, it's 0.06 plus x, and 0.06 plus 0.06 plus 0.009 is 0.069. So the pH would be the negative log of 0.069 instead of 0.072, which was the case with the approximation. I get 1.16. So that's different. That's different from 1.14. So I protest that the multiple choice problem here, they seem to be expecting you to say 1.14, but I think that's not accurate. It should be 1.16. But anyways, either way, 1.14 is the choice that's closest to 1.16 of all these choices. So 1.14 it is for these guys. So that's number 15. Thanks. Bye, Noah.